I'm Alec, a robotics graduate student at the University of Maryland. This semester in autonomous robotics class, each student was challenged to build and program a robot capable of navigating a 12-foot by 12-foot arena, finding and picking up 3 red, 3 green, and 3 blue colored blocks, and transporting them one at a time to a special section of the arena. The robot must do all of this autonomously within 10 minutes and while avoiding the decoy black, white, and yellow blocks. This has been one of the most challenging projects I've ever worked on because it required integration of computer vision, motion control and planning, localization, sensor fusion, Internet of Things, and mechanical design. Altogether, I wrote 1,600 lines of Python code for this project. This video summarizes the major milestones in the development of this robot, all the way from initial construction and setup to the grand challenge itself. All right, let's go through some of these videos together. First, in the setup and construction, we had to set up the Raspberry Pi, reinstalling Raspbian, getting connected to Wi-Fi, and then using the camera for the first time just to take a time lapse, learning how to use the camera, and then getting a little bit more advanced with the camera, doing a little bit HSV masking to track an object. That's just the green circle there in the stoplight. And then upgrading a little bit to do this arrow, using some different OpenCV functions to find the corners of the arrow so I could tell what direction it was facing where it says it in the top left. Now, the disassembled picture of all the parts of the chassis here, we'll get into a time lapse. This took place over a couple days in class. First, we're putting on the wheels. The encoders were a little bit tricky because of the small screws on the front left and back right. Putting the top plate on, mounting the battery and the motor driver, and then soldering up the kill switch so that I can turn off the motors if anything goes wrong. Mounting the Raspberry Pi on top, and then getting all the motors and encoders wired up to the motor driver. And then this is the next class period. Everything looks a little bit different. I used some more sturdy standoffs, and then wiring the Raspberry Pi up to the motor driver. And now we'll see the robot driving around a little bit. This is just teleoperation, so I'm using WASD on the keyboard to control it. It's nothing intelligent, but it's still a win for me that it's actually driving and working. Now, in that same class period, we're assembling the gripper so that it can actually pick up the objects, and wiring the gripper up to the Raspberry Pi. So the Raspberry Pi sends a PWM signal that you'll see up there in the top left corner, which drives the servo motor. And here's the first demo of the robot driving and operating the servo. Now that most of the robot has been assembled, I started adding some intelligence to it. So first, just driving forward straight for 12 inches and then stopping using the encoder counts to know how far it's gone. And then the Arduino Nano with the inertial measurement unit to tell what the heading of the robot is. And you can see as I move the robot, just turning it, the line will go up and down on the serial plotter, showing its angle. So that spike right there is the robot crossing from 0 to 360 degrees, which was a little bit tough to deal with later on. Now combining the inertial measurement unit with the encoder counts to drive perfectly straight, which is harder than it looks, a lot harder, for 59 inches or 1.5 meters. Now I'm challenging the robot to drive in a 1 by 1 meter square, first here without the inertial measurement unit for control, and then second with the inertial measurement unit. And you can see right now it's not doing a very good job of driving in a square. And that's because the IMU is so critical to effective control. Because without it, the robot doesn't have much of an idea where it is. You can see it's off there by like 0.4 meters. This is the path it took without the IMU. Now with the IMU, notice the start position, it'll go right back to that. We drive forward for 1 meter, turn almost perfectly 90 degrees, and then turn again perfectly 90 degrees, this time not coming close to the wall. You can already tell that it's a much better square, which really goes to show how critical the IMU is. This would be so much harder without that. Off by like 1 inch there in the plot. So now we're gonna move on to the camera, using the HSV masking to find the blocks. First, the red block. See how the red block there is picked out of the frame so that the robot can go find that one. And now going to the green, just moving those hue sliders And finally, going to the blue, again moving the hue sliders to change the thresholds at which it will mask out the image. Putting that into practice now with the controls, the robot is instructed to go for the green block. It'll use the camera to find it with the HSV mask and then drive straight to pick it up. But the problem is it doesn't know quite how far away the block is. So here I'm calibrating the robot to know how far away the block is based off of its height in the camera frame. Here's calibrating the robot again with the ultrasonic sensor because they're not exactly a one-to-one relationship, real distance to measured distance. I also noticed during some testing that occasionally the decoy black, yellow, or white blocks would get stuck under the gripper or over here on the side as the robot's moving. So I 3D printed these two pieces to help prevent that from happening. Now the robot is in its final form. Everything's built, everything's tested, it just has to go run in the Grand Challenge. So reminder for the Grand Challenge, the robot has to start in the start zone, go find a red block, move it to the construction zone, and then green, blue, red, green, blue, red, green, blue, in that order, all 9 blocks. And if it picks up a black, a white, or a yellow, it loses a point. So this right here is just the path that the robot mapped out for itself, its trajectory during the Grand Challenge. Here's the robot's official run through the Grand Challenge. I'll leave this mostly on its own with some light commentary here and there. So this overlay is the map that I showed you before, showing where the robot thought it was versus where it actually is in the video. When it goes to pick up this green block, you can see it's actually going to turn around and catch the black block in front of the green, which is unfortunate because that made it lose a point, but I'm still happy that it ends up getting all 9 blocks in the end. I also want you to notice right here, when it turns to face the 2 walls after it places a block, that's it using the ultrasonic sensor to ping its distance off those 2 perpendicular walls to relocalize its location. Without that, the encoders in the IMU would eventually drift a little bit, and by the end of the run, it might be 6 feet off its location estimation. So that ultrasonic sensor is really crucial for relocalizing each time. Now we're in the home stretch, just the last 3 blocks. This video is sped up 400%, by the way. The actual run took 7 minutes and 50 seconds for the robot to finish. So when it goes to get this green one, you'll see that the yellow is in the way, so it doesn't see it. And so it goes to a predefined search point to look for blocks from a different angle in case there's something in the way, like what just happened. Here we're getting the last block, little over 7 minutes, placing it, and then not necessary, but it's going to go back to the start just to celebrate. And so this is actually the robot's perspective of what it's been seeing the whole time. You see the text changes color depending on what its target block is. It'll say what it thinks its current location is in X, Y, and theta, and then its current task, whether it's going to pick up a block or verifying that it's got one. All done? Thanks for a great semester.